Alright, welcome to the notes on Pythagorean theorem, radicals, the converse of Pythagorean theorem. Today here's the objectives for today. These are in your notes. The warm-up, we're going to simplify the following radicals. So these should be pretty easy for us to do. Square root of 16 is 4. Square root of 36 is 6. Square root of 18 is a little bit more difficult. It's easy to do in our calculator, but we're looking to simplify radicals. Okay. Some of you may remember how to do this. It's 3 times, whoopsie daisy, 3 times the square root of 2. If you don't remember how to do that, don't worry, we're going to come back and review that Algebra 1 lesson here shortly. The simplest form of the radical, before we remind you how to do it, some things to keep in mind. No perfect square can divide the number underneath the sign evenly. No radicals can be found in the denominator. Okay, that's important. And no negatives. Okay, so those are big keys when simplifying radicals, that you're looking for those three things. A list of perfect squares is really useful. You can make this list from memory. You can do it using your calculator if you need to, but this list is useful when simplifying radicals. It's useful because what we're looking for is the largest perfect square that goes into, or that is a factor of, what is underneath the radical. So let's go back to the square root of 18. The square root of 18, the largest perfect square that is a factor of 18 is 9. So we can change square root of 18 to the square root of 9 times 2. Okay, that's the same thing, square root of 9 times 2. We can then change this to square root of 9 times the square root of 2. The square root of 9, we all know, is 3. And this, when we read this as 3 times the square root of 2. Now your calculator is really useful here, just as a tool to check your work. If I put in 18 and I take the square root of it, I get 4.242641. If I then take the square root of 2 and multiply that by 3, I get that same 4.242641 number. So even though it doesn't simplify the radical for me, it's a really quick, easy way to check my work. So I'll give you a second, pause the video here, and let you work on these. Simplify these radicals: square root of 8, square root of 48, and square root of 72. Pause the video now. Okay, so I've given you a chance to simplify these radicals. The square root of 8 is 2 times the square root of 2. The square root of 48 is 4 times the square root of 3. The square root of 72 is 6 times the square root of 2. Just if you needed a quick reminder, the largest perfect square that goes into 8 is 4. The largest perfect square that goes into 48 is 16. And the largest perfect square that goes into 72 is 36. That's how I did those. How to square a square root. If I were to square the square root of a, okay, then I get square root of a times the square root of a, which equals just a. The reason I'm showing... What was that noise? Did you drop something? Okay. So that's how we do that. The reason I'm showing you that is, we'll get to in a second, but just take a look at these real simply. The square root of 20 squared is just 20. The square root of 10 squared is just 10. And the square root of 25 squared is just 25. This should make sense. This is probably the easiest one for us to look at. The square root of 25 is 5. 5 squared is 25. Okay, so that's how that works. Reason I'm showing you that is that you have to do that in order to do what's called rationalize the denominator. Okay, when we rationalize the denominator, what that means is that it has a radical on the bottom. We can't have that. We already said that. And so we're going to get rid of the radical mathematically. Okay. Whoopsie daisy. Sorry, skip the page there. Who says whoopsie daisy anymore? Anybody? Nope. Okay. So we're going to multiply the top and bottom by the denominator. We're going to multiply it by a form of the number 1 that is useful to us. It has to be the same on the top and bottom because a number divided by a number is 1. And that means that we're changing the way the fraction looks. We're not changing its actual value. When we do this, we multiply straight across. 2 times the square root of 2 is just that, 2 times the square root of 2. And then on the bottom, square root of 2 times the square root of 2 is 2. Now here I need to check and see if I can simplify this fraction, which I can. You could think of this as 2x over 2, where you would simplify the 2's into 1. They would divide to 1 and have just the x left. Same idea here. This is just going to equal the square root of 2. That's another one you can check in your calculator. Okay, you can do math on your calculator that's useful here. This is square root of 2 is equal to that, and then 2 divided by the square root of 2. Okay, so we can do 2 divided by 2 square root. Whoopsie daisy. And there, I said it again. This calculator has trouble doing it. Let me get out my Casio calculator. Casio. If I do 2 divided by the square root of 2, I get the same thing as if I take the square root of 2. They're the same exact number. And that'll work on a TI also, surprisingly. Okay, so next page. You try one. Go ahead and pause the video here and see if you can do one of these on your own. Okay, and when we unpause now, take a look at this. I'm going to multiply both sides by the square root of 5 over the square root of 5, because that was the denominator. The top becomes just 3 times the square root of 5. The bottom becomes just 5. Because this is not a fraction I can simplify, that's it. That's my answer. The Pythagorean theorem. You guys have been working with the Pythagorean theorem for a really long time. You should know this pretty well. It's not too complicated. It's the a squared plus b squared equals c squared. And that works because we have a right angle here. The Pythagorean theorem is the square of the sum of the legs is equal to the square of the hypotenuse. Parts of the triangle. A and B we commonly refer to as the legs, and C is the hypotenuse. Alright. Find the missing side. So using the Pythagorean theorem, let's find the missing side of this triangle. So this is 8 squared plus 4 squared equals, that's an x squared. So we have 64 plus 16 equals x squared, and that's 80 equals x squared. At this point, we're going to take the square root of both sides. So x equals the square root of 80. But you got to ask yourself, is 80 simplified? So let's go to our list of perfect squares. Is there a perfect square that goes evenly into 80? And the answer is yes. 16 goes in evenly. So that we would change this to square root of 16 times the square root of 5, which is 4 times the square root of 5. And again, you can check that in your calculator to make sure that's done correctly. The reason this says careful here is because the most common mistake students do is they put the variable that we're looking for by itself, but you got to remember that it's leg plus leg equals hypotenuse. So this is x squared plus 7 squared equals 11 squared. So we have x squared equals 121 minus 49. X squared equals 72. And then it's the square root of 72, which that's one that we've already done today. That's 6 times the square root of 2. And again, you can check that if you need to. This one's a little bit harder. I'll do the setup, and then you'll pause the video and see if you can solve this one on your own. This is x squared plus 3 times the square root of 5 squared equals 12 squared. I'm going to pause the video now and see if you can solve that one on your own. Okay, so let's take a look at what you've done. 3 times the square root of 5 squared is probably the hardest part about this. The nice thing is that for those of you that have a graphing calculator and know how to use it, or if you know how to do the math, 3 squared is 9, square root of 5 squared is 5, so 9 times 5 is 45. If you're not sure of that, you can put it in your calculator, use parentheses when you put it in, and you get 45. So then I have x squared plus 45 equals 144. From there, it's pretty easy. X squared equals 99. Largest perfect square that goes into 99 is 9. So that becomes 3 times the square root of 11. Not too hard. The converse of the Pythagorean theorem. So we've done inverse, converse, contrapositive. Okay, Pythagorean theorem says that if you have a right angle or a right triangle, then a squared plus b squared equals c squared. The converse now says that if a squared plus b squared equals c squared, you have a right triangle. So it's just the same thing in the reverse order. To determine, we use that to determine whether or not a triangle is a right triangle. Okay. We use it to determine whether or not a triangle is a right triangle. So you're given some sides here, and you want to determine whether or not it's a right triangle. So you simply you take the two smaller sides. I know that the hypotenuse has to be the longest side, so the hypotenuse goes by itself, or the potential hypotenuse. This is what we're checking right here. 8 squared is 64. 15 squared is 225. 17 squared is 289. 64 plus 225 is 289. 289 is equal to 289. So yes, this is a right triangle. Simple as that. So you try. Determine whether or not this is a right triangle. First step you're going to need to do is figure out which two sides are the shortest sides. Pause the video here and work the problem. Alright, so you've unpaused the video. Let's take a look and see if we have figured out if this is a right triangle or not. While you guys paused the video, it was amazing. There was a calc lesson going on in here that was riveting. Riveting stuff. Alright, so let's take a look. You've done the setup here. This is square root of 41 squared plus 20 squared equals 21 squared. Again, nice thing about your calculator, you can put this right here. Square root of 41 squared is 41, plus 20 squared is 441. 21 squared is also 441. So is the triangle, whoops, there we go. Is the triangle a right triangle? Yes, it is. Hooray! Let's take a look at this. We can also determine whether or not, given sides, whether or not a triangle is obtuse or acute. So now we have three choices. Is it right? If it's right, they're going to be equal. If it's obtuse, then the legs will be less than the hypotenuse. If it's acute, the legs will be greater than the hypotenuse. So all we do, it's pretty simple. You just set this up, the two smaller sides squared. And then I like to put like an empty circle where I'm going to put either equal, less than, or greater than. If in your head just now you said the words alligator mouth, then you need to see me after school. So I'm going to do the setup for each of these, making sure that I add the two smaller sides. Put my circle, and then equal to, I don't know why I'm putting equal also. That doesn't make any sense. Ignore that. Yep, that never happened. Okay, circle there, because we don't know if they're equal. That's what we're checking to find out. So 2 squared plus 3 squared, and then 5 squared, 4 squared plus 12 squared, whoops, 9 squared, and then 12 squared, and then 7 squared plus 8 squared, and 9 squared. Also, a good habit to get into is to check and make sure these equal, that the sum of the legs of the two smaller sides is greater than the remaining side, because if it's not even a triangle. We don't have to do the problem. So let's take a look here. 7 plus 8 is more than 14. So 7 squared is 49. 8 squared is 64. 49 plus 64 is 113. 14 squared is 196. So this is greater. Because the legs are less, this is obtuse. 2, 5, and 3, this is not a triangle. 2 plus 3 is not more than 5. So that's not even a triangle. 4 squared plus 9 squared, this is 16. This is 81, so that adds up to 97. This is 144, so it's less than, so this is obtuse. And 7, 8, and 9, this is 49, this is 64, this is 81. That one's pretty easy. This is, we've had 7 and 8 before. That's also 113, that's bigger than 81, so that's greater than, so this is acute. Alright, let's take a look at the next page. What is the Pythagorean theorem? Just quick reminders to yourself. Jot this down. This is a squared plus b squared equals c squared. The converse of the Pythagorean theorem is used to determine whether or not a triangle is right. So there you have those. We can also use the converse to determine whether or not a triangle is obtuse or acute. We're all done. Those are the notes. 6D is the classwork we'll be working on together. So I will see you next time.